Free body diagrams are a super important part of this course, and they'll also be a really important part of courses moving forward. So if you haven't seen them yet, I'm just going to go over some of the basics. So essentially, let's say you have a system. Let's say you have a slope here and you have a whole bunch of boxes along your slope. Like that. And let's call this A, B, C, D. And let's say the question wants to identify what's happening here with block A. So I create a free body diagram to isolate block A from the overall system. So my free body diagram, I'll redraw the body that I'm interested in. So in this case, it's block A. And I'll draw all the forces that are being applied on it. Actually, I'll put an external force here. So let's put an external force here, force here. So on block A, I've got this external force here that's coming down. I also have the weight of A that's pushing down. And then block A is going along this slope here. So when I isolate block A, I'm essentially taking away this line as well. And I have to replace that line with the force that it was applying on A. And that force is always perpendicular to the path of motion. So here we would have the normal force here. This would be the normal force of A. If the block was flat, on the flat ground, the normal force would be pointing upwards. If it was a straight wall, let's say the block was going against a vertical wall, when you took out that wall, when you take that wall away, the normal force here would be perpendicular to where the wall was. So that's just important for the direction of the normal force. And then, but we also have to consider the forces due to these blocks. Now, instead of considering the mass of each block, we replace that with the normal force that's occurring between block A and B here. So that means we have a normal force here that I'm going to call normal force AB. In this case, we don't have a problem, so we don't really know friction, but let's assume there's some friction. So the friction would oppose the motion, which means the friction here, we would have a force of friction that's opposing the path of motion. I'll redraw this slope here so it's easier to see. And those would be all of the forces in this diagram. Putting some axes is always a good idea. Sometimes if you have a slope, you actually put the axes along the path of the slope. So we could make that our x direction, and we could make this our y direction. You can also solve it. You could also say that your x direction is straight and your y direction is vertical. Either way works, but this is a lot easier for solving these problems actually if you just define the x direction as going in the same direction as that slope. And then sometimes you also add your angles here, so you might add the angle of your force here. But that's basically a free body diagram. You only include all of the external forces. Depending on the problem, you might have to draw more than one free body diagram if it's asking you for information about different bodies. So don't assume that you only need one free body diagram. You'll need a free body diagram for each particle that the question is asking you about. And sometimes you might need two free body diagrams. So let's say a question is asking you, maybe the question is asking you for the force here between A and B, and then it's also asking you for a force here. You would isolate a different body for those different types of questions. A quick note on directions of friction. So if you have, let's say you have a person pushing this box here, a person pushing on the box. The friction along this box, so we're going to assume that the box is going to move that way. The friction will oppose the motion, so you have your force of friction moving this way. The friction on the person itself is actually going to be going in this direction. Let's say you have a tractor that's pushing the box. This is sort of like the front part of the tractor that's pushing against your box, and it's still going in the same direction. Here the force of friction is still going to be opposing the motion, but for these wheels would be turning clockwise, right, to move forward, to push the box forward, which means that right at the surface of the ground where the wheel is in contact, it means that the wheel is moving this way, so the force of friction of the wheel will be going to the right, same as pushing to the right for the person. So this force of friction up here for the person is allowing the person to stay on the ground and push against the box, right? Similarly down here with the tractor that's pushing the box. But let's say you had, so this was your tractor. Let's say you had a tractor that was getting pulled. So again, we have a tractor here, but this time some cable is pulling the tractor, it's getting pulled, and these tires are slipping. That now means that your force of friction is going to be moving to the left. So here you have no slip, here you have slipping. Because when these tires here are slipping against the ground, they're no longer rotating and creating that traction. They might as well just be a box on the ground, which means that the force of friction is simply opposing the motion. That's important to understand. I'm going to move this up so that we can talk about impending motion. So impending motion is really, really important to consider. Impending motion. So most of our systems will start from rest, and then the question will ask you what happens when the system is released from rest. And let's make a really simple system. So here we have a box along the ground. If we draw our free body diagram, and we have a force P pushing against it, and this is a box of mass, box of mass M. So now, if we draw the free body diagram of this, we would have our box here, we would have our P, we would have our weight, which is mg is equal to weight. So make sure you're not writing mass here. These are all forces, which means it's the weight, it's not the mass of the box. Then we have our normal force upwards, and then we have our force of friction opposing the motion. So this was normal, and this was the force P. Now, the force of friction, you have to be a little bit careful with it because it can be sneaky. So in general, the force of friction is equal to mu n. But there's two different types of mu's. You can have mu s and you can have mu k. Mu s is the static one, and mu k is kinetic. Usually the static one is slightly higher. And this makes sense because it takes a little bit more force to get the box moving than to keep it moving once it's moving. But the force of friction also can't exceed the force that's being applied to it. What do I mean by that? So let's say the mass of our box is equal to 10 kilograms, and I'll say mu s is equal to 0.5 and mu k is equal to 0.2. Let's start off with a case where our P is equal to 20 newtons. In this case, our normal force, so if we do summation of Fy, we end up with minus W plus normal is equal to 0. The reason why this is equal to 0 is because our box is not floating, it's not moving upwards. So there's no acceleration in the y direction, so it has to be equal to 0. So this means that our normal force is equal to our weight, which is equal to mass times gravity, which is equal to 98.1 newtons. Now we'll do summation of x, and we have summation of x is equal to mass times acceleration in the x direction. So then we would have P minus the force of friction is equal to mass times acceleration. Before we do this, we have to figure out if there is acceleration. So what we need to find out is this P big enough to compensate any potential force of friction? I'm just going to move the screen up. So we start off by saying max is equal to 0, which is equal to P minus force of friction. In this case, that's saying that force of friction, which is equal to, and we're assuming it's not moving, so it's equal to the static mu s. It's equal to mu s n, which is equal to P. So our mu s times normal would be mu s was 0.5 times normal, which is 98.1, is equal to 42.0. Oh, sorry. It's equal to 49.05. So this would be the force necessary to get the box moving, and our force is equal to 20. So this means that we don't have enough force to get the box moving. So there is no acceleration. But let's say, I'm going to move this up again. Let's say we have P is equal to 100 newtons. And our equation was 0 is equal to P minus the force of friction. So that's equal to 100 minus the normal force times mu s. So it's 100 minus 98.1 times 0.5. So then 100 minus 49.05 is equal to 50.95. This here tells us that we have enough force to overcome that friction. We have enough force. So this tells us that we have motion. Now, since we have motion, we go back and we use our kinetic coefficient of friction. So our kinetic coefficient of friction, mu k, was equal to 0.2. So now we say summation of force in the x direction is equal to mass times acceleration. So we have P minus force of friction is equal to mass times acceleration. I can move this up quickly. So then we have 100 minus mu kn is equal to the mass, which was 10, times A. So this is 100 minus 0.2 times 98.1 is equal to 10 times A. Then A is equal to 8.04 meters per second squared. A really important thing to note here is that when you're doing the impending motion analysis, you use mu s. When you're doing, then if you find that there is motion, then you use, for acceleration analysis, you use mu k. So I can't just go up here and say, oh, I have 50.95, that's the force to overcome friction, because here I was checking with the static friction. When you're actually doing the motion analysis, you have to use your kinetic friction. One more thing that you can use this for is to figure out the direction of motion. So sometimes you'll have a problem and you're like, is it moving to the left or to the right? You can use impending motion analysis to figure out what your system's doing and the directions of motion before you get into your kinematics.